Hello guys, welcome once more to another video in our YouTube channel. So in today's video we are going to be looking at the CASPA mock of 2024 for the math paper 2 question 2 precisely. So this question came from the topic sequences combined with integrals, so I just termed it integral sequences. So there are 4 questions in total in this particular question 2, and in the next upcoming slides, I'm going to show you how to analyze each of these questions. So stay tuned as we proceed. Alright, so let's begin with the first question. Roman 1, it reads, show that 0 is less than or equal to in less than or equal to 1 divided by n plus 1. And we have been given that n is a natural number and the sequence or the integral in is equal to the integral from 0 to 1 of x to the n times the square root of 1 minus x dx. Alright, so how do I show that an integral is bounded between two different functions, or how do I prove this? Okay, so the first thing you have to have in mind whenever you approach such questions is that you need to begin with the interval where the variable belongs to. So here, since I am integrating from 0 to 1, it means that my x is in the interval 0 to 1, which can be written in inequalities as such. So x belonging in this interval means that 0 is less than or equal to x less than or equal to 1. The bounds are included because they belong to the domain of definition of the function. Okay, because when x is 0, 1 minus x will exist. That's the square root of 1 minus x will exist. And when x is 1, also the square root of 1 minus x will exist. So that's why we have to include the bounds in the interval. All right, now from here we are going to start by bounding the square root. Okay, inside the square root we have 1 minus x. Now we have information about x, so we can clearly get the information about 1 minus x. We start by multiplying all through by negative so that we get negative x. Then later on we now add this 1 all through, so we get the 1 minus x. Okay, so when I multiply by negative, there is a rule that says that the inequality signs are going to change direction. So rather I am going to have negative 1 is less than or equal to negative x less than or equal to 0. We know that negative 0 does not exist. So now I'm going to add 1 all through. When I add 1 to negative 1 is equivalent to saying 1 minus negative 1. If I add 1 to negative x is equivalent to saying 1 minus x. And if I add 1 to 0 is equivalent to saying 1 plus 0. Now everything will boil down to 0 is less than or equal to 1 minus x less than or equal to 1. Now if 1 minus x is between 0 and 1, then clearly the interval that 1 minus x belongs to is a positive interval, because if you are between 0 and 1, then you are clearly positive and the square root will exist. All right, and the square root function is an increasing function. All right, so it means that we can take the square root all through, and since it is an increasing function, the inequality signs will remain intact. So from here, if I take the square root all through, the square root of 0 is 0. I'm going to be left with the square root of 1 minus x, and the square root of 1 is 1. Now I'll need to multiply all through by x to the n so that I get the integrand, okay, before I integrate all through and get my I of n. So multiply all through by x to the n. Remember that x is in a positive interval, n is a positive number, so x to the n will be positive, so the inequality signs will not change upon the multiplication. So I multiply all through by x to the n. This is what I get. Then since all these functions, all these 3 functions are all continuous and defined in the interval 0 to 1, then we can integrate all through from 0 to 1 with respect to x. So integrating 0 from 0 to 1 with respect to x, integrating x to the n root 1 minus x from 0 to 1 with respect to x, and integrating x to the n from 0 to 1 with respect to x. The lower bound of the integral will give us 0. The middle is going to give us I of n. That's the definition of I of n from the beginning. And the upper bound of the inequality will give us, if you integrate x to the n, we just have to use the power rule where we add 1 to the power and we divide it by the power plus 1 from 0 to 1. Now if I replace x with 1, 1 to the power n plus 1 is 1. So we are going to have the upper bound to be 1 divided by n plus 1. when we replace x with 0, everything becomes 0. So it therefore means that I of n lies between 0 and 1 divided by n plus 1. So we have successfully proven the Roman 1 of the equation. Now let's go to Roman 2, which is asking us to show that I of n is a decreasing function. Here we are going to use two different methods, and you choose the method best for you. Make sure you comment in the comment section which method you prefer or which method is more easy. Alright, so let's begin with the first method. And now, generally, to prove that a sequence is decreasing, we need to prove that the difference between the n plus 1 term and the n term of the sequence is always negative or 0. That's the meaning of decreasing. If it was strictly decreasing, then we use a strict inequality. So here we are required to show that I of n plus 1 minus I of n is less than or equal to 0. Okay, so using the first method, we use the information we have had, which is I of n is between 0 and 1 over n plus 1. So if I of n is between 0 and 1 over n plus 1, it therefore means that I of n is a positive sequence, but it is less than 1 over n plus 1. So I can just say that I of n is actually less than 1 over n plus 1, bearing in mind that it is a positive sequence. Okay, from here I can look for I of n plus 1. Alright, so if I of n is less than or equal to 1 over n plus 1, to get where I of n plus 1 lies, I just need to replace n with n plus 1. So if I replace n, alright, if I replace n here with n plus 1, I am also going to replace n here with n plus 1. The n plus 1 here we add up with 1 to give us n plus 2, and then we have replaced n with n plus 1. It therefore means that I of n plus 1 will be less than or equal to 1 divided by n plus 2. Now if I subtract the two equations by taking I of n plus 1 minus I of n, it therefore means that I need to take 1 over n plus 2 minus 1 over n plus 1. And I maintain my inequality sign less than or equal to. Now if I simplify 1 over n plus 2 minus 1 over n plus 1 using normal bringing the fractions together, I look for the LCM. This is what we are going to have, and when we simplify everything, the numerator is going to give us negative 1, okay, while the denominator will give us n plus 1 times n plus 2. So it therefore means that I of n plus 1 minus I of n will be less than or equal to negative 1 divided by n plus 1 times n plus 2. But we know that n is a natural number, therefore it is positive. So n plus 1 as well will be positive, and n plus 2 will also be positive. When you multiply two positive quantities, the result is positive. So the denominator of this ratio is positive and the numerator is negative. And if we take negative divided by positive, it's going to be negative. So everything will be less than or equal to 0. Negative means that you are actually to the left of 0. Alright, so if you are less than or equal to 0, we can just clearly conclude that I of n plus 1 minus I of n is less than or equal to 0. And if I of n plus 1 minus I of n is less than or equal to 0, then the sequence I of n is decreasing. That is what we are required to prove. Okay, like I said, this is the first method. So what about the second method? The second method, I'll go straight to the point. I will use the integral itself. So I'm going to do I of n plus 1 minus I of n using the integral. So I of n plus 1 minus I of n. Now, the first integral here is actually I of n plus 1. How do we get it? We come to I of n and we replace n with n plus 1. We get I of n plus 1. Now, the second integral is I of n. But if you look at these two integrals, you realize that the first integral can also be written as the integral from 0 to 1. In fact, the integrand can be written as x to the n times the square root of 1 minus x, then everything multiplied by x, right? Because x to the n plus 1 is the same as x to the n times x. Now, you also see that this term here is also part of the integrand of the second integral. Alright, so and the two integrals have the same limit from 0 to 1, so we can combine the two integrals together and we factorize what is common. Okay, so doing that, we basically just have the integral from 0 to 1. What is common is x to the n times the square root of 1 minus x. When we factorize it from the first integrand, we are going to be left with x, and when we factorize from the second integral, we are going to be left with -1. We are going to be left with 1, but now there's a negative sign. In fact, if we multiply everything, okay, we are going to get back to the previous step. Now you realize that the integral will totally be negative. Why will it be negative? Now this was happening. Since x is between 0 and 1, it means that x is less than 1, okay? And when x is less than 1, now in the first part of this question, we proved that x to the n times the square root of 1 minus x is positive. Here is it. If 0 is less than u, it means that you are greater than 0, so you are positive. So this portion in the black coloration is positive. Now what about x minus 1? Now remember that x is between 0 and 1, alright? In fact, come to this portion and you're going to realize that if we subtract 1 on both sides, then x minus 1 will be negative. So if I subtract 1 on both sides, I'm going to have that x minus 1 will be less than 0. So this other part is less than 0, and we are multiplying two of them, alright? So the integrand here will automatically be negative because I am multiplying a positive function and a negative function, so the result will be negative. And if I am integrating a negative function, my result will be negative. By definition, the integral of a negative function is also negative. Okay, so everything here just implies that in plus 1 minus in is less than 0, which means that I of n is a decreasing sequence. Alright, so comment in the comment section which method is preferable. Is it method 1 or is it method 2? Or which method have you easily understood? Alright, let's move on to the next part of this question. Alright, so Roman theory, we have to deduce that the sequence I of n converges and we need to find its limit. So the convergence theorem simply says that if a sequence is monotonic and bounded, then it converges. Alright, we clearly saw that it is bounded because it is bounded. Here is the recall. It is between 0 and 1 over n plus 1, and it is also decreasing as we proved. And since you are bounded and monotonic, whether increasing or decreasing, you clearly converge. Now, how do we find the limit of the sequence? We need to use what we call the sandwich theorem or the squeeze theorem. It says that if a sequence is bounded between two other sequences and the limit of those two other sequences are the same, then the limit of that sequence is that limit. Now this sequence is bounded between 0 and 1 on n plus 1. So I'm going to find the limit of 0 and the limit of 1 on n plus 1. And I compare. If the two limits are the same, it therefore means that the limit of the sequence involved is that limit. And remember that the limit of a sequence is a limit at plus infinity. So let's begin. The limit as n tends to plus infinity of 1 over n plus 1 is 0, because the denominator will be turning will be very big, so its reciprocal will be very small. Now the limit of 0 is also 0. It therefore means that from the squeeze or the sandwich theorem, the limit of the sequence in is equal to 0. Now the last part of the equation, we need to prove that for every n greater or equal to 1, 2n plus 3 times I of n is equal to 2n times I of n minus 1. So we are going to use integration by parts to prove this. Now you realize that if you look at I of n minus 1, like let us try to get I of n minus 1. To get I of n minus 1, all we need to do is to replace n here with n minus 1. And before n becomes n minus 1, then we have differentiated x to the n. Okay, if I differentiate x to the n, I just need to drop the power, then I take x raised to the power n minus 1. So this is going to give me what my u is going to be and what my dv is going to be before I use integration by parts. So u is a function which you are going to differentiate, while dv is a function you are going to integrate. So clearly I'm going to let my u to the x to the n, so that when I differentiate I get n times x to the n minus 1 dx. Now my dv is going to be the remaining part of the integral, which clearly will be the square root of 1 minus x dx. I wrote it as 1 minus x. Remember that there is a dx attached to this. Okay, now I wrote it as 1 minus x to the power half, so I can easily show you how it can be integrated. Okay, so how do we integrate this? This is what we do. We need to differentiate the interior. When we differentiate 1 minus x, we get negative 1. Here is a negative sign outside here. Now next we have to divide it by the power plus 1. So if I take half plus 1, I am going to get 3 over 2, but that 3 over 2 is supposed to be in the denominator. So 1 over 3 over 2 is the same as 2 divided by 3. Then we multiply it with the very function to the power plus 1. The power is 2 and we need to add 1 to it. So integrating, basically this is what we get. Okay, now integration by parts says that our I of n is uv minus the integral of v du. So, and we need to also impute the limits of integration because it's a definite integral. Alright, all we need to do is we need to replace v and du with their respective functions that we have gotten above. Okay, so I of n will be equal to, now let's start with u. Our u is x to the n. Okay, so here is u, x to the n. Now we need to multiply it with v, and our v is negative 2/3 times 1 minus x to the half plus 1. Half plus 1 is 3 divided by 2. So the negative sign is there, and then now the 2/3 times 1 minus x to the 3 on 2 is there. We need to impute the limits of integration from 0 to 1. Now in the integration by parts formula, there is a generic negative sign. But now since I am multiplying it with v du and my v has a negative sign, then everything becomes positive. That is why we have a positive sign. Now we are going to remove all the constants out of the integral. 2/3. Now let's first of all look for v du. Now this is du, okay, and this is v. So v du, this is what we do. We multiply all the constants first and we put it out of the integral. The two constants are n and 2/3, so that is 2/3 n. Alright, now the remaining part of du is x to the n minus 1 dx. Here is it. Here is x to the n minus 1 and here is dx. And then now the remaining part of v is 1 minus x to the power half plus 1. Here is it. 1 minus x raised to the power half plus 1. Now all we need to do is simplification. That's what we need to do. If we are able to simplify everything, then we are going to get the proof. Okay, so let's start simplification. We start by replacing 1 as the upper bound. Okay, we replace x with 1. Now 1 minus 1 will give us 0, so everything is 0. Next we replace x with 0. Clearly this portion, there's an x here, so it's going to give us 0. So it means that this first portion here will give us 0, meaning that our I of n will just be 2n on 3 times the integral from 0 to 1. Now I've done something inside here. You see this portion in black, it is the same as sending it to the denominator by indices. Now this portion in black also is the same as multiplying this quantity with it that is, we have to separate it by indices. We take 1 minus x to the half times 1 minus x to the power 1. If we multiply, we can use the same base and we just add their powers. Okay, so that's the work of simplification. So what do we do next? I can rewrite this as I group all the terms in black together, so that I have now 1 minus x to the power half is the square root of 1 minus x. Now I'm going to have 1 minus x divided by x as one term, and then x to the n times the square root of 1 minus x as another term. Now what happens is that 1 minus x on x is the same as 1 over x minus x over x. 1 over x stays as 1 over x, and then x over x stays as 1. So 1 over x here is the same as x raised to the power negative 1. So basically we are going to replace this quantity here with x to the negative 1 minus 1. Okay, so doing that, we have x to the negative 1 minus 1. Now let us distribute this x to the n and also the integral. The 2n on 3 is a constant, so it multiplies both terms. So 2n on 3 will multiply the integral from 0 to 1. If I multiply x to the n times the square root of 1 minus x with x to the negative 1, I will just need to combine the two x's together that have the same base. So I'm just going to add their powers. So taking n plus negative 1 is the same as taking n minus 1. So this is the first integral. Now we are also going to take this same quantity and we multiply with negative 1. Remember that 2n on 3 is still a factor, so we have negative 2n on 3 times the integral of the quantity, because when the quantity multiplies with negative 1, the negative sign is outside and the quantity remains unchanged. Now you realize that this quantity here is basically I of n minus 1. So this quantity is I of n minus 1, while this quantity is I of n. It therefore means that if I multiply all through by 3, I'm just going to be left with 2n here, and also I'm going to be left with 2n here. So 3I of n will be equal to 2n times I of n minus 1 minus 2n times I of n. Now all I need to do is I need to add this quantity on both sides, and then I factorize I of n, and I get the proof. So if you do this, if you factorize I of n from these two quantities, you're going to have I of n times 2n plus 3 to be equal to 2n times I of n minus 1, which is a proof. So guys, thank you guys for watching. See you guys in the next video. If you have difficulties with solving this Roman 4, make sure you check the description of this video. You're going to see many other videos concerning integration by parts in further maths, that is reduction formula. You're going to see like 4 different videos explaining this concept. If you have problems with sequences and series, still check the description of this video, and you're going to see a series of many questions on sequences, on a series of many videos on sequences and series that you can watch from the beginning to the end. Make sure you like this video, you share the video with your friends, and you also comment.